All right, we finally made it. Chapter 2. We're going to talk about new material today, limits specifically, or an introduction to limits. We do this by using the concept of velocity, both average and instantaneous velocity. Instantaneous velocity we look at all the time. Well, every time we drive a car, when we look at our speedometer, that is our instantaneous speed, the speed that we are doing right at that instant. And that instantaneous velocity changes as we change our speed or push our foot up and down on that accelerator. Average velocity would be, let's just say I'm traveling down a straight road. I don't want to deal with direction in this. So, well, actually I am dealing with direction by saying I'm going down a straight road, but I'm going down a straight road, traveling at 50 miles an hour, and then for a while I go, ooh, I'm going to speed up a little bit, so I travel 70 miles an hour for a while. Let's just say that I managed to do this in such a way so that the distance that I travel divided by the time equals 60 miles an hour. That's what they're talking about here, is you're traveling some speed, different speeds, but your average, the distance divided by time, worked out to be 60 miles an hour. So that's average velocity. And instantaneous was whatever we saw on our speedometer at the time we were traveling down the road. Example 1 is about launching a rock upwards from the ground. And seeing as it's traveling at a speed of 96 feet per second, I probably didn't throw it. So here's our formula. At least I didn't throw it anyway. Here's our formula for that rock. At any time on this x-axis, that is time, and I plotted this with my TI-84 calculator from 0 to 6 seconds. 0 to 6 seconds I believe is what I did. Yep. And I think I chose to go from 0 to 150 counting by tens in my window, just so that you'll know where I'm at. They want you to calculate the average velocity at time 1 second to time 3 seconds. And that would give you the slope of this secant line. So the slope of that secant line is the velocity. It is that distance, because I'll get the difference in the y's, and the y's is the distance in feet, distance over that time frame, hence average velocity. I used my TI-84 calculator and set up my table so that I could get these values fairly easily. So the slope of that secant line, which is also known as average velocity, is the difference in the y's over the difference in the x's. So formally written, that would be s of, for this one they want me to do s of 3 minus s of 1, or that height, and then the difference in the y's, the difference in the x's on the bottom, I have the difference in the y's on the top, 3 minus 1. I go to my table and see that at 3 I was at 144 feet in the air. 1 second I was at 80 feet in the air, all divided by 2, and that yields an average velocity of 32 feet per second when you crunch those numbers. And play the same game again. This is my A part. Play the same game again for B. And let's see what that line would actually look like, just so I can get some idea. I want it from 1 to 2. So from 1 here up to 2. Notice how the slope of this line is steeper. So I'm expecting that average velocity to be a little greater. And the closer I get, let's say, to this 1, notice if I was to do, say, from 1 to 1.1 or 1.2, something like that, that line gets fairly steep right there. And what that's saying is that this velocity here at the very beginning is greater and the velocity or the speed is slow. The rock is slowing down as it approaches the highest point, at which point the velocity here would be 0. If I was looking at my speedometer at that particular point, my speed or my velocity would be 0, and after that point my speed starts going down or becomes negative. So let's get that B question completed. Just doing the same thing that I did before. This would be the height at 2 seconds minus the height at 1 second, because I'm doing the B part. 2 minus 1. The height at the 2 second mark is 128 minus the height at the 1 second mark, that is 80 all over 1, and this would be 48 feet per second. Nice. And your textbook has one of these cool interactive graphs, so I can't not show you this. It shows you a beautiful little picture of the secant line from 1 to 3 seconds, the difference in the y's over the difference in the x's there, and there is the time from 1 to 2 seconds. Notice from 0 to 3, 0 to 2, 0 to 1, watch this, what the slope of that line does. And then from 1 to 4, notice that that velocity, average velocity value becomes less, because, and I can see that by looking visually at the slope of that secant line. In example 2, they want me to look at this velocity at this point when the time is 1 second. And they want me to estimate it. What they did was they created this nice little table here, and in this table they chose the secant line to get closer and closer, the 2 points that I was choosing for my secant line to be closer and closer to 1. And notice as I did that, or as they did that, that value came closer and closer to 64. Another word for having those 2 points get closer and closer to a single point, or get closer and closer to 1, is called a tangent line. And a tangent line, we'll look at this cool interactive graph once again. As these points, notice as these 2 points that graphically get closer and closer to 1, I get closer and closer to this magic number of 64, and that would be what the slope of that tangent line. And the tangent line means that the line doesn't hit your curve in 2 places, but it hits it in 1 place, and it is a unique line, meaning that there's only one of them that would be able to do this. And it is that slope of the tangent line that we are concerned with in our calculus course. We'll be talking about the slope of the tangent line over and over again. So we saw both a table version of looking at the slope of that tangent line, and here's a graphical version of looking at the slope of that tangent line. It's a secant line when it is 2 separate points, and as we get closer and closer to it being a single point, or in other words a limit, then it becomes a tangent line. Cool. And the next set of graphs is just reiterating again that secant line being the 2 points and the slope of those, slope in between those 2 points versus the slope of just that 1 point, which would be the secant line. And you'll notice they're saying here that the slope as those 2 points, those 2 points approach a single point, would be our limit or the instantaneous velocity.